high pressure. Yeah, for water. Okay, so the procedure we talked about was something like starting from vapor region somewhere here, okay, then going vertically because we kept the temperature constant and increasing the pressure, right? So we go upwards. As you can see here, we process the vapor liquid region, so that's when the transition from vapor to liquid occurs. And yeah, as you said, if we keep increasing the pressure, we could go right into the solid region, but look at the pressure here is something like gigapascal. So the pressure is very, very high, and that's in the log scale. Okay, so very high pressure you need for compressing liquid into solid. Yeah, so normally we let's say that in most applications we don't see that kind of transition by just increasing the pressure. For solid to appear, it's much easier to move horizontally, that is changing the temperature. Okay.
Is it practically possible?
Pardon?
Practically possible with this?
It's possible, of course, because that phase diagram is basically from experiments. So people have observed that kind of transition, that the pressure is just very high, in the order of gigapascal. Yeah, so you have to go to that high pressure to see that kind of transition.
So one more question.
Yes.
So if we increase the pressure, but also we increase the temperature, no constant temperature,
Pardon? If you increase the pressure?
and also the temperature.
And also the temperature?
Yeah.
Yeah, so you just move diagonally.
When it convert from vapors to liquid, then
Vapor to liquid.
yeah.
Yeah, so you can certainly do that, right? So from the vapor phase, then you increase pressure simultaneously with decreasing the temperature, then you go like that.
Increasing temperature.
Or increasing the temperature, then you would depend on the ratio between the two, right? You could end up in the liquid phase or going straight into the supercritical fluid region. Right? So if you go like that, oops, maybe I should sit down. If you go start from this point and then go like that, you still go into the liquid region, right? But if you increase the temperature quite quickly, then you go somewhere there. It's right into the gas region or right into over there, the supercritical fluid region. Yeah, so you can just read from the phase diagram. Okay, so come back to this phase diagram. Okay, so this is pressure XY diagram of hexane and octane. Okay, now this is a mixture, two components, hexane C6 and octane C8. Okay, vertical axis is the pressure, the horizontal axis is the mole fraction of hexane. Normally, by convention, but you don't have to stick to this convention, but normally people do this. The mole fraction to be represented on the horizontal axis is normally the lighter component, the more volatile component. So in this case, hexane, C6, right? So mole fraction of hexane, X, mole fraction of hexane in the liquid phase, Y, mole fraction of hexane in the vapor phase. Normally we use this set of symbols, right? So X for the liquid phase, Y for the vapor phase, okay? And from this diagram, we see that there are three regions. Okay, three regions. The top region is when our system is in liquid phase. Oh, the temperature is fixed. at 473.15 Kelvin. Okay, that's 200 degrees Celsius. So every point in this diagram is at 200 degrees Celsius. Okay, top region liquid, the bottom region vapor. Okay, that is you can just use your common sense here. High pressure, molecules are close to one another, so they tend to condense into liquid. So high pressure, you should expect liquid. Low pressure, you expect vapor. Okay, so you can just use your common sense here. And then in the middle, in this region here, between the liquid and vapor regions, that's where we have vapor and liquid coexisting in the same system. That is where we have vapor-liquid equilibrium. Okay? And then normally when we use this diagram, we draw a tie line. Okay, a tie line. The tie line is basically, in this diagram, the line at a constant pressure linking mole fraction of hexane in the liquid phase to that in the vapor phase. Okay, that is normally what we do when we read this phase diagram. Okay, this tie line tells you the composition of the liquid phase and the vapor phase when your system has two phases coexisting. Okay, maybe it's easier to look at the animation after this one. Okay, so yeah, let's start from this. Okay, let's start from this point here. It means we prepare in this vessel a mixture containing 40% hexane and the rest 60% octane. Okay, the pressure is 4 bar, 400 kilopascal, that's 4 bar. Okay, according to this phase diagram, it is well in the vapor region, so your system is entirely vapor. Okay, Z and Y. Okay, so Z is something that quite a lot of people are not quite clear about. Y is the mole fraction of hexane in vapor phase, right? You can see that this is vapor, so we say Y is 40%, 0.4, right? Z is something we call overall composition or overall mole fraction. Z1 is overall mole fraction of hexane, component 1, that is hexane, okay? So overall mole fraction of hexane in your system. Overall means even if your system splits into multiple phases, you don't care if you have multiple phases there. You just count only hexane in your system and then divide that by the number of moles of your entire system. Or you can also think about it as the mole fraction of hexane when you prepare this system. Okay, so right now you have only single phase in your system. So Z, the overall mole fraction of hexane, or the mole fraction as prepared, is the same as Y, which is the mole fraction of hexane in the vapor phase. Okay, you see the difference when we increase the pressure and the system splits into two phases. Okay, so the condition here is quite boring, so let's increase the pressure. If you go to 795 kilopascal, right on the red curve here, okay, actually I should have said this earlier. Red curve is dew point curve, right? The red curve is a dew point pressure curve, okay, dew point pressure curve. And the blue curve is the bubble point pressure curve, okay? If you recall the concepts of bubble point and dew point, right? So red curve is a dew point curve. In this case, we're talking about pressure, so it's dew point pressure curve. Okay. Even though it says dew, which refers to liquid droplets, right? But actually, it means the last point where vapor could exist alone. If you go past this dew point into that region, the middle region, you will start to see some liquid. That is why this curve is called dew point curve. Okay, if you cross this boundary, you start to see some liquid droplets. So that red curve is called dew point curve. Okay, and then the blue curve here is called the bubble point pressure curve. It's bubble refers to vapor or gas, right? But actually, the bubble point means saturated liquid. It is the last point where you will still see liquid only in your system. To understand why it is called bubble point, we have to actually start from somewhere up there, right? When we are in the region of fully liquid. Okay? If we decrease the pressure a little bit down here, start to cross this blue curve into the middle region, we'll start to see some bubbles in our system. Okay, so that is why the blue curve is called the bubble point curve. Okay? Right, let's continue our discussion at this 795 kilopascal. Okay, so right now we are on the dew point curve. Our system is saturated vapor. It means it is quite very ready to condense into liquid. If you increase the pressure even a little bit, you start to see some liquid droplets, which are called dew. Okay, so right here, Y1 and Z1 are still the same. Okay, don't worry. Let's increase the pressure a little bit. Now, this is what we're talking about. The topic of today's lecture: vapor-liquid equilibrium of mixture. Okay, the pressure is now 910 kilopascal. There, that's the coordinates of our system right now. Okay, so the pressure is 910 kilopascal. The overall mole fraction Z1 remains the same at 40% hexane. Okay, because well, this is just physical separation. There's no transition from one component to another. So you could imagine if we have 40% hexane, 60% octane in our system, even if these two split into two phases, the overall composition, okay, no matter the distribution, will still be 40% hexane. Okay? However, if we talk about the composition in liquid and vapor phases, these two phases will have different compositions. Okay? X1 refers to the mole fraction of hexane in the liquid phase. Okay? So we can read that from the diagram. From that point, it's about 33%, something like that. Okay? So liquid phase here, lying at the bottom of your vessel, has 30% hexane in it. Okay, and the rest 70% in the liquid is octane. On the other hand, in the vapor phase, okay, in the vapor layer over here, Y, the mole fraction of hexane in the vapor phase, will be about 53%. Okay, so your vapor consists of 53% as hexane. The rest, 47% is octane. Okay? And how do you find X and Y? You use pi line. Okay? So that's the pi line. A horizontal line, which means constant pressure, linking the blue curve to the red curve. Okay? Linking the bubble point curve to the dew point curve. That's your pi line. And then you read the value of X from the blue curve, and then the value of Y from the red curve. Okay? You can also remember it like this. Okay? So X is the mole fraction of hexane in the liquid phase, right? Well, the blue curve is adjacent to the liquid region. Okay? So it makes sense, right? That point is on the curve that is adjacent to the liquid region. So it represents mole fraction of hexane in the liquid phase. Okay. Similarly, Y, okay, Y is on the red curve, which is the boundary of the vapor phase. So Y represents mole fraction of hexane in the vapor phase. Okay, so you can just remember it like that. It represents the mole fraction of the region, the curve is boundary of that region. Okay? And now we can see that x, y, and z all have different values. Okay, so z, again, right, z is the overall composition. In other words, the composition as prepared. When you prepare at the start, you have 40% hexane in your system. So no matter how the components distribute into two phases, the overall composition remains the same. Okay? However, the x and y would be different because when we have vapor-liquid equilibrium of mixture, the composition of the liquid phase and the vapor phase will be different. And this is something that we exploit a lot in chemical engineering. This is the fundamentals for phase separation, for purification. For example, the distillation column exploits this phenomenon. Okay? When you have vapor-liquid equilibrium of mixture, the composition of vapor and liquid is different. So if you keep doing this multiple times, you can purify your vapor along the red curve. So your vapor becomes enriched in the more volatile component. Okay? And you can also do the same for liquid phase, going to the left-hand side, and then you have more the heavier component in your liquid phase. So basically that's how distillation column works. Okay? Right, now we have x, y, and z. And then the concept that can be confusing. Okay? The ratio of the amount of the two phases. Okay? So we just talked about x, y, and z. Those are compositions. Okay? Those are compositions. How concentrated hexane is in the liquid phase or in the vapor phase. Now, NV over NL. Okay, N is the number of mole. Okay, NV over NL would be the number of mole of your vapor phase entirely. Okay, that means including both hexane and octane. To NL, the number of moles in the liquid phase, including both hexane and octane. Okay, that ratio NV over NL can be found by finding this ratio, A over B. Okay? A is here, difference between x and z. So basically just z minus x, that is your A. Okay? Over B, B is y minus z. That equation is called lever rule. Okay? Lever. Okay? Lever rule, L-E-V-E-R, lever rule. In Thai is Kanna. Okay? Lever rule. Basically, it's for material balance. So if you wonder where does this come from, you can try doing some material balance. It will end up at this equation here. So from phase diagram, okay, you can also find the ratio of the two phases, okay, NV over NL. That is how much you have for vapor to liquid phase. Okay. The problem with this lever rule is that you have to do some crossing, and when I say crossing, it means like this: NV over NL, right? So vapor to liquid. You have to find ratio of A to B. A is now adjacent to the liquid region, and then B is adjacent to the vapor phase, to the vapor region. So it kind of cross one another. Okay, so vapor to liquid equals to the distance from Z to the liquid region to the distance from Z to the vapor region. So you can see that it crosses one another like that. So it's a bit confusing, but that is how it is as revealed by material balance. Okay, so let's try applying this in some extreme case here. If I go back to this situation, okay, let's apply lever rule here. Okay, let's find NV over NL of at these conditions. NV over NL, that is the ratio of number of moles in the vapor phase to in the liquid phase, right? Then we actually see the answer here. It's all vapor, right? But we can still apply the lever rule here. Okay, so Linear rule NV over NL is A over B, right? What is your A? What is your A in this example? A is the difference between Z and X, right? So your Z is 0.4, X is quite close to 0.2, so your A would be 0.2 approximately, right? B, and what's B?
0.
B is 0, right? Exactly, because B is the difference between Y and Z. So B is 0, NV over NL equals A over B, so it's 0.2 divided by 0, so it's infinity, well, which means your system is entirely vapor. Okay? Then we go back to this situation here. A and B can now be defined as a finite number now, right? Because it's 0.4 minus 0.33 over 0.55 minus 0.4, something like that. So it's a finite number over here. So we define the ratio of the two phases. Okay? So that's what happens when you have vapor-liquid equilibrium of mixture. Okay, so the very important thing to keep in mind is that when you have vapor-liquid equilibrium of mixture, the composition of the two phases are different. Okay, so that's very important to keep in mind. When you have vapor-liquid equilibrium of mixture, the two phases, the liquid phase and the vapor phase, have different compositions. Okay, so that's most important to keep in mind. Right. Then, if we keep pressing the piston into the cylinder, of course we hit bubble point. Okay, we hit bubble point here. So over there, the pressure is 1 megapascal. Okay, 1,000 kilopascal is basically 1 megapascal. That is bubble point. It means the system has just been compressed to entirely liquid. The liquid in this system is saturated liquid right now. Okay? When it is entirely liquid, Z and X and Z are the same. Okay, X and Z are now the same. And then we also have Y1. Y1 is, let's say, theoretical composition of the vapor phase, which doesn't exist yet in this example. Okay? Or maybe you can think of Y1 as the composition of the first bubble that would appear if you lower the pressure very, very slightly. Okay, so that's bubble point. Your system, if your system is exactly at the bubble point, your system is entirely liquid. But if you lower the pressure only very slightly, the first bubble appears. Okay, the first bubble appears. The composition of the first bubble will be, at that point, Y1. Okay? Right. And then if you keep pressing it further, nothing interesting occurs anymore because it's what we call subcooled liquid. There's no phase separation. The composition remains the same. Okay, so that is kind of physical phenomena that occur for vapor-liquid equilibrium of mixture. Okay. And then we study thermodynamics of phase equilibrium so that we can find some mathematical relations of the system, and then we can use that relation to predict the properties of phase equilibrium of your mixtures. Very importantly, let's say we specify temperature and pressure, and then we must be able to find the composition of the liquid phase and the vapor phase. Because when we can do that, then we can design our phase separation equipment like flash gun, and we can also do something more complicated like a distillation column. Okay, so that's the purpose of thermodynamics of phase equilibrium of mixture. Okay, so we start to go into more details here. Okay, to explain what happens thermodynamically for phase equilibrium of mixture, we will apply something that is quite similar to phase equilibrium of pure component. Okay, you've seen this diagram before, in one of our previous lectures. For pure component system, right? The Gibbs free energy curves cross one another where phase transition occurs. Okay, for example, here, liquid curve, vapor curve, the crossing is here, so that's your boiling temperature. In other words, phase transition occurs when Gibbs of the two phases are equal. Okay, in mixture, we have something like that, but it will be slightly more complicated. Okay, so let's look at this diagram here. Now we'll try to explain the PXY diagram through Gibbs free energy diagram of mixture. Okay, the inset there is the PXY diagram of our same system, our previous system, the hexane and octane at 200 degrees Celsius. Okay, the large diagram is the Gibbs free energy versus XY. So the vertical axis is now Gibbs free energy, not pressure. Okay? And then we have two curves. Okay, we have two curves. The blue curve is for the liquid phase, and then the red curve is for the vapor phase. Okay? These two curves represent the Gibbs free energy when at different compositions. When the temperature is at 200 degrees Celsius, and right now the pressure is at 4.5 bar. Okay, the Gibbs free energy of liquid at different composition is represented by the blue curve, and that of the vapor is represented by the red curve. Okay, right now at this pressure 4.5 bar, according to the PXY diagram, it's at that pressure represented by the dashed line. Okay, so dashed line is at 4.5 bar. Okay, it means at whatever composition you should have vapor only in your system. Okay, so at 4.5 bar, according to this PXY diagram, this dashed line is entirely in the vapor region. So it means at whatever composition your system will be in the vapor phase. Okay? And then let's look at the Gibbs free energy diagram. It is consistent because the curve for the vapor phase lies below the curve of the liquid phase at any composition. It means vapor phase is more stable. Okay, so according to the second law of thermodynamics, if your system has two choices, it will go to the choice where Gibbs free energy is lowest. Okay, according to the second law of thermodynamics, your system will try to lower its Gibbs free energy when possible. So in this case, between the liquid phase and the vapor phase, it will go to the vapor phase because the Gibbs free energy is lower. And that is true for any composition. Okay, for any composition. Okay, now let's increase the pressure. So when we increase the pressure, it will be higher than 4.5 bar. Okay. When we increase the pressure, this is what we should expect. Okay, so because we have this relation, Vg equals Vdp. Okay, V is always positive, right? It's molar volume. It cannot be a negative value. It means when we increase pressure, Gibbs free energy increases as well in the same direction. Okay, and how fast the Gibbs free energy rises with the pressure depends on the molar volume of that phase. Can you guess which one goes faster with this pressure? According to this equation, between liquid and vapor, which one will rise faster when you increase the pressure? It has to be the one with larger V, right? Between liquid and vapor, the phase with larger molar volume will have its gives free energy increase faster when the pressure increases. And of course, the vapor phase has larger molar volume. Okay, and normally it's about 800 times larger than the molar volume of liquid. So when you increase the pressure, the red curve, the curve for the vapor phase, moves up quite clearly, while that of the liquid phase more or less stays in the same place. Okay, because the molar volume of liquid is very small compared to that of vapor phase. So that is V is quite close to zero compared to that of vapor. Okay, so when you increase the pressure, the red curve goes upwards quite quickly, while the curve for the liquid phase more or less stays in the same place. Okay, so let's increase the pressure. Now we go to 5.6 bar. Okay, so as you can see here, the blue curve remains more or less in the same place, while red curve is now raised to where the left end coincides with the left end of the blue curve. Okay, so 5.6 bar is quite special because according to the PXY diagram, on the left end here is where octane, the left side, the leftmost side of the diagram means 0% hexane, it means 100% octane. Okay, at that point, that is the vapor pressure of octane at 200 degrees Celsius, where octane starts to be able to transform into liquid phase. Okay, over there. Now look at the Gibbs free energy diagram. The red and blue curve coincide at the same point. Now recall what we've learned in 2 weeks ago. Phase transition of pure component occurs when Gibbs free energy of the two phases are equal. Right? So that is consistent with the PXY diagram there. So that's the vapor pressure of octane, right? This shows that at this pressure is a vapor pressure of octane. Okay? Well, this is still boring, it's pure component, right? We are talking about this pure component there. Now let's increase the pressure further. Now 10 bar, okay, 10 bar. The red curve and the blue curve now cross one another. Okay, let's look at the PXY diagram first. In the PXY diagram, it says in a certain range of your composition between the red curve and the blue curve, you have vapor liquid equilibrium at this pressure of 10 bar. Okay, if your composition is well in this region, your system would be entirely liquid. If your system is has a lot of hexane in it, maybe somewhere here, it's entirely vapor. Okay, but if your system has about more or less the same amount of hexane and octane, you will have vapor liquid equilibrium. Your system splits into two phases of vapor and liquid, right? And that is actually a range, you see. It's between maybe 0.4 and 0.6. It's a range, okay? It's a range. However, if you look at this Gibbs free energy diagram, okay, let's apply our previous understanding, which is actually wrong in this case, but let's do this anyway, okay? In our previous understanding, we say our system would try to be in a situation where the Gibbs free energy is lowest, right? So according to this diagram here, in this region to maybe about 0.5, blue curve is below the red curve. It means the Gibbs free energy of the liquid phase is lower than that of the vapor phase. So your system should be liquid up to where you have 50% hexane in your system, right? And then if you have more hexane than that, red curve is below blue curve, it means your system should prefer to be in the vapor phase, right? If you apply our previous knowledge. However, this is wrong, okay? As I told you earlier, we have to do something more for mixture. Yeah? This is wrong because it is inconsistent with the PXY diagram. As you can see here, the entire liquid region and the purely vapor region is separated by a range of composition, not just a single value of composition here. So it contradicts one another, as you can see here. Okay, that is because we have to do something more about this diagram for mixture. Okay, what we do is that we need to draw a straight line. Okay, just touching. Okay, the blue curve and the red curve. I will zoom in this region a little further. You could imagine that these are two curves. So if you zoom in, it should be more or less like that. Okay, so we need to do that region. Okay? That straight line should just touch the two curves. Okay, you draw a straight line touching the two curves. Now we have two touching points. So on the blue curve and on the red curve. Okay, and what is so special about this straight line? Okay, refer back to when we talk about solution thermodynamics. We have this graphical method for determining the partial property. Okay? These two curves are the Gibbs free curve for liquid solution and the vapor solution. Okay? If we draw a straight line touching, forming a tangent at a particular point here, that end of the straight line would give you the partial Gibbs free energy of component 1. Okay? And this end will give you the partial Gibbs free energy of component 2. With your vapor is at that composition. That composition is about 1.6 in the vapor phase. Okay? However, at this point on the blue curve, the composition is 0.4, but the tangent is still the same as the tangent that we did for the vapor curve. Okay, so it means even on the liquid side, at that composition, G1 bar is the same as the G1 bar in the vapor phase. Okay, G2 bar in the liquid phase is the same as the G2 bar in the vapor phase. Okay, because we use the same line here, which touches the two curves. So from this diagram, G1 bar of the liquid phase equals that in the vapor phase. G2 bar in the liquid phase is the same as G2 bar in the vapor phase. Okay, so now maybe you start to see some connection here. Okay, for mixture, the criterion for phase equilibrium is not the Gibbs free energy of the entire phase, but rather the partial Gibbs free energy of the same component. Okay, so that's your phase equilibrium criterion for mixture. Okay, in other words, when you have phase equilibrium for your mixture, when your system actually reaches the equilibrium, this is the condition. Okay, the partial Gibbs free energy of the same component in the two phases must be equal. Okay, partial Gibbs free energy of the same component in the two phases must be equal, and this must be true for all components in your system. Okay, that is the criterion for phase equilibrium for mixture. Okay, so instead of just Gibbs free energy, you need to use partial Gibbs free energy in mixture. And again, partial Gibbs free energy is basically just the Gibbs free energy of a single component when it is diluted in something else. Okay, so you use partial Gibbs free energy when you describe phase equilibrium of mixture. Okay, and then let's discuss this further. Okay, this alone still do not explain why we have phase split in mixture. Okay. Now we need to draw something a little bit further here. I got green line here. Okay. On that tangent line, but just between the touching point on the blue curve and the red curve. Okay. Now that green line, this may be a little bit difficult to understand, but just give you a sense. Okay. So this green straight line represents the Gibbs free energy of this entire system when you have two phases. Okay? So when you have two phases, vapor phase with 60% hexane and liquid phase with 40% hexane. Okay, when you have two phases in your system, the Gibbs free energy of the two phases are simply the average of the two weighted by the number of moles of the phases. Okay, so when you do that, basically it's a straight line connecting the two compositions. So your green line here represents the Gibbs free energy of your entire system consisting of two phases. Okay, now look at the position of the green line here. It's below both blue curve and red curve. So whatever that is on this green line is more stable, more favorable thermodynamically. And because this green line represents that system having two phases, it means the system having two phases is the most stable, okay, in this situation. It is more stable than having entirely liquid or entirely vapor. So the system prefers to be in vapor and liquid equilibrium at this particular condition. Okay, so basically what I'm saying here is that when the system consists of vapor phase and liquid phase, two phases, the Gibbs free energy is lowest. Okay, it's even lower than liquid alone or vapor alone. So the system prefers to be in vapor-liquid equilibrium. Okay, so that's the thermodynamic explanation of why vapor-liquid equilibrium forms for mixture, and also you can see that it also explains why the composition of the liquid phase and vapor phase are different. Okay, because it needs different composition in order for the partial Gibbs free energy of the same component to be the same in both cases. Okay, and then if we increase the pressure further to 18 bar, well, that's similar to what we did earlier for octane. That's the vapor pressure of hexane. Okay, and from Gibbs free energy diagram, you see that the red curve and the blue curve coincide at the right hand side. So that's vapor pressure of hexane. So yeah, that is more or less what happens thermodynamically in terms of Gibbs free energy of solutions in the two phases when we vary pressure and going through transition from vapor to vapor-liquid equilibrium into all liquid phase. Okay, so we'll transcribe this into mathematics, okay, so that we can use that for calculations. Not really difficult. Okay, so let's start from this idealized case. Okay, let's say we have a system consisting of two phases, phase alpha and phase beta. So it can be solid, liquid, solid, vapor, liquid, solid, whatever. It doesn't have to be just vapor and liquid. So we'll just call phase alpha and phase beta. Okay. As I said earlier, when we have phase equilibrium, the composition of the two phases are different. Okay. We'll develop an equation that describes the criterion when we reach phase equilibrium. Okay, so the concept is just like as we discussed earlier, but now we will do something fully mathematics so that it is kind of certain. Okay, right. So what I want to show you here is that maybe it's a bit confusing, but I'm going to talk about this anyway. Okay, let's look at this diagram here. Okay, as I said earlier, that green line, okay, the solid green line there represents the Gibbs free energy of vapor liquid system at equilibrium. Okay, the important point here is that this solid green line represents vapor liquid system at equilibrium. Okay, when I say at equilibrium, the composition has to be exactly here of the two phases. So liquid phase has about 40% hexane, vapor phase about 60% hexane. If the composition of the two phases aren't at this value, your system is not at equilibrium. And it can be shown on this diagram here. That green line represents a system consisting of vapor phase and liquid phase, but the composition aren't at the equilibrium composition. See, vapor phase instead of being at 0.6, I say let's try vapor phase having only 0.4 of hexane. Okay, and then liquid phase over there something more, a little bit more than 0.6. When we draw a straight line here, you see that Gibbs free energy of your system is very high. Okay, very high. So this is highly unfavorable for your system. Your system wants to lower its Gibbs free energy. So how can it do, or what can it do in order to lower the Gibbs free energy of your system? By doing mass exchange between two phases. Okay, so hexane in the liquid phase is too much, right? So transfer hexane to the vapor phase, and then transfer octane from vapor phase to liquid phase. When it does that, yeah, the curve just go down, 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 and then, oops. Yeah, eventually it will go to that point. Okay, so that point is the lowest possible. If you think about it, that green line is the lowest point possible because, well, you have blue curve, red curve. The lowest point possible is having a straight line. Just touch those 2 points. So that solid green line is the lowest point possible in your system. So that's your equilibrium. That represents your equilibrium. Okay? So we develop a mathematical equation to describe this situation, alright? So we will have to write an equation showing Gibbs free energy of your system containing vapor and liquid phase, okay? We just write dNg equals NVdP minus NSdT plus that term which represents mass transfer or mass.
Is it the most?
Yeah, mass transfer is meant to describe it that way. Right? But we write 2 equations, okay, 2 equations, one for phase alpha, the other for phase beta, and then we add the 2 together, okay? When we add the 2 together, the left-hand side, dNg alpha and dNg beta together is just dNg, okay? Because we have change in the Gibbs free energy in the alpha phase and then change in the Gibbs free energy in the beta phase. If you combine the 2, it's basically the change in the Gibbs free energy of your entire system.
That's true.
Okay, so change in alpha phase plus change in beta phase basically is change in your entire system. Okay, now we consider our change at constant temperature and pressure. So we don't need these 2 terms in both equations. So dP is 0 because constant pressure. dt is 0 because we consider only at constant temperature. The only terms that have to survive the addition into this final equation is these 2 terms. Okay, the terms that represent mass going in and out between 2 phases. Okay. Okay. Now we define our systems to have only 2 phases. So when there is mass going in or out of one phase, it means that mass going out or in the other phase. Okay? So let's say component 1 leave phase alpha, it has to go to phase beta. Okay? So there's kind of a relation. We can express that relation by this equation here. So dni alpha equals minus dni beta. So increase in one phase equals decrease in the other. Okay? Now we use this expression in that one. Okay, so basically we write dni beta as minus dni alpha. Then we can rewrite that equation into this one. Okay, so it simply become dng equals sigma of gi alpha bar minus di beta bar multiplied by dni alpha. Okay? At equilibrium, the Gibbs free energy is at minimum. Okay, it's at minimum. And our system will try to go to that minimum by mass exchange. Okay, by mass exchange. So, if we look at it graphically, okay, let's say we have just two components in our system. That's our Gibbs free energy. That's number of moles of component 1 and for component 2. That's the lowest point. Okay, the lowest point is somewhere over there. The mathematical criterion for that minimum is that the derivative of Gibbs free energy with respect to N1 is 0, and the derivative of Ng with respect to N2 is also 0. In other words, the derivative of Ng with respect to the number of moles of all components must be 0. Okay, so we do that. Right? dng by dni alpha equals 0. Okay, and according to this equation, it means di alpha bar minus di beta bar is 0. And this must be true for all components. Okay, so this is basically derived from the fact that we want to find the minimum. Okay, we want to find the minimum, so it leads to this criterion here, this condition. In other words, that's our phase equilibrium criterion. Okay, so gi alpha bar equals gi beta bar. Okay, as we said earlier, graphically. Okay, but this is derived mathematically, so it's more certain. We trust in mathematics. Okay, right. So in other words, as I said a couple of times already, so in human language, it means the partial Gibbs free energy of the same component in the two phases must be equal. That is phase equilibrium criterion for mixture. Okay. Okay, so so far we have used GI bar as a symbol for partial Gibbs free energy, right? However, in thermodynamics, we also have another quantity with this symbol mu I. Okay, mu I. Mu is actually chemical potential. Okay, chemical potential. Theoretically, it's not exactly the same as partial Gibbs free energy, but the numerical value is the same as partial Gibbs free energy. So we can just say that these two symbols can be used interchangeably. Okay, so GI bar, partial Gibbs free energy, is kind of the same as chemical potential, and you see both. Okay, in textbook or in something about thermodynamics, they are basically the same, even though technically they are largely the same. Okay, the chemical potential, that is the term potential in it, right? If you think about gravitational potential, what do you think about? What can you interpret gravitational potential? It is something that if an object has that gravitational potential, it has a tendency to go to somewhere with lower gravitational potential, right? This is in pretty much the same sense. Okay, so the partial Gibbs free energy also represents the chemical potential. It means if you have two phases, okay, if you have two phases, and your two phases are not at equilibrium at the moment, it means in one phase there is too much of some component in it. Okay, it means that component in that phase has too high chemical potential, and it will try to move to the other phase. Okay, you try to move to other phase. When does it stop moving? When the chemical potential of that component is the same in both phases. That is when you reach equilibrium. Okay, so yeah, go over this again, right? For example, you have liquid and vapor, and it is not at equilibrium because you just mix them up manually, for example. In your vapor phase, maybe you have too much hexane. Okay, so thermodynamically, it means the chemical potential of hexane in your vapor phase is higher than that in the liquid phase. So hexane will try to migrate to the liquid phase to lower its chemical potential, and then the last point where it can move is when the chemical potential of hexane in the two phases are equal. And when the chemical potential of hexane in two phases are equal, it stops moving now. It means your system is at equilibrium, and that represents the equal chemical potential of hexane in two phases. Okay, so that criteria can be imagined in this way as well. Your system is at equilibrium when chemical potential of the same components in two phases are equal. Okay, so the components stop moving across spaces. Okay, now we have criterion. Okay, now we see that we need partial Gibbs free energy to do some calculations about phase equilibrium for mixture, right? So we must be able to describe partial Gibbs free energy mathematically. Okay, so that we can form some model about it. We start by using ideal gas model as a basis. Yes.
Is it possible that both of the phases will diffuse into each other?
One phase is diffusing to
Each other. Like the gas and the liquid phase, they are both mixed.
well, if at equilibrium there must be liquid and vapor, then mass transfer is just from vapor to liquid or liquid to vapor.
Like it's diffused, the vapors are mixed into the liquid.
It's not only the component, but yeah, when a component from vapor phase diffuses into liquid phase, it undergoes phase change as well. So vapor into liquid, so it also condenses basically from vapor into liquid. And then when a component in liquid phase wants to go into the vapor phase, it has to evaporate as
So
well.
they cannot exist in the solution form.
If vapor and liquid are stirred vigorously, well, they are still two phases, but form something like a turbid suspension, you can imagine. Yeah, something like that. So we still describe that as two separate phases. It's just that the vapor phase is just small, tiny bubbles dispersed in the liquid phase. And if you leave it for a while, as you can imagine, vapor will just try to bubble and form two distinct phases anyway. Okay, so we start from ideal gas mixing. Okay, we have seen this situation already, but I will go over this again very quickly. Okay, so we have gas 1 and gas 2, right? Here gas 1 and gas 2 separated by a partition. Then we consider gas 1 and gas 2 separately. Okay, we remove the partition, right? Of course, gas 1 and gas 2 will mix into one another, and basically, as I said earlier, mixing is, well, when considered separately, it's just expansion of one gas into another, right? So it's an expansion of a gas to the full volume of your vessel. We use this basis for determining the partial Gibbs free energy as well. Okay, so Gg equals VdP minus SdT. Okay, we will do this at constant temperature. Okay, I didn't write that here, but yeah. So this mixing, okay, is carried out at constant temperature. So when gas 1 expands to the full volume of your vessel, the pressure decreases, right? Starting from system pressure, down to partial pressure of gas 1. Okay, and partial pressure is Y1P. Okay, so the pressure decreases when the gas expands. Okay, basically, according to that thought experiment, the partial Gibbs free energy is simply the Gibbs free energy when the the pressure of that component decreases to partial pressure. Okay, so when gas 1 mixed into gas 2, its pressure, which is now called partial pressure, decreases. Okay, so because there is decrease in the pressure that component 1 experiences, there is a change in its Gibbs free energy. Okay, so its new value of Gibbs free energy is basically the partial Gibbs free energy of that component. So dG equals VdP. Okay, we don't need that term because we do this at constant temperature. So integrate dG equals VdP. On the left-hand side is partial Gibbs free energy. Okay, now I just write mu, it's shorter anyway. Okay, so that's partial Gibbs free energy minus GI, which is the Gibbs free energy of pure component before mixing. Okay, of pure component equals integral of VdP from system's pressure to partial pressure of that component, YIP. Okay, so for ideal gas, this integral is very simple because V for ideal gas is RT over P. Okay, so do the integration very quickly. That's your integral, right? So it becomes RT log YI. Okay. So this is basically, if you do the integration, that's RT log YIP over P. Okay, so it becomes RT log YI. That's your partial Gibbs free energy based on the ideal gas model. Okay, this equation says the partial Gibbs free energy of component I based on the ideal gas model is basically Gibbs free energy of that component when it is pure plus a correction term when it is not pure. Okay, and that correction term is simply RT log YI, the mole fraction of that component. Okay, very simple. Partial Gibbs free energy of component I based on the ideal gas model is basically Gibbs free energy of that component when it is pure plus a correction term when it is not pure. And that correction term is simply RT log YI. Okay, and then this is just for plotting a curve. Okay, if you want to plot a curve for the entire solution, okay, we use this relation. Gibbs of entire solution. Right? So that is no subscript. No subscript means this represents the property of your solution. It is GIG, Gibbs free energy of your ideal gas mixture equals the weighted average of partial properties, right? So of partial Gibbs free energy. We substitute this into that equation, then we get this one here. This one can be used to plot this curve here. So basically, this is how I obtained this plot here, okay, in previous diagram. Okay, just want to show that to you very quickly. And then if you use this equation to plot your partial Gibbs free energy, you can also have this kind of diagram. So yellow curve for component 1, blue curve for component 2, and these straight lines are just to show that they still obey the graphical methods for finding the partial properties that we discussed earlier. Right? For example, here when the mole fraction of ethanol is 0.3 over there, right? You draw a tangent line here, okay, at that point. That end of the tangent line represents partial Gibbs free energy of component 1, exactly on the yellow curve, right? that for partial Gibbs of component 2 exactly on the blue curve. But well, not very important this bit, okay? And this is just to show that there's certainly difference between the Gibbs free energy from the ideal gas model and from a more accurate model, right? So red curve for ideal gas, if you want to obtain the real value, the black curve, which is hidden behind the blue curve, okay, you need to add a correction term here, and you could imagine to transform ideal gas property into a real property. What do we need? A residual property, right? Because residual property is basically the difference between the real value and the ideal gas value. So, yeah, the difference here is the residual Gibbs free energy of solution. We will need to find that from cubic equation of state to get accurate value of the Gibbs free energy. Okay, so that is why we need cubic equation of state for this phase equilibrium as well. So because we need to find the residual Gibbs free energy so that we can correct the value from the ideal gas model to the real value. Okay. Now, when we start talking about residual Gibbs free energy, we have to talk about fugacity. Okay. So fugacity is something that has been a meme in chemical engineering a lot. If you follow some Facebook pages about chemical engineering memes, you know that there are quite a lot about fugacity, right? People try to interpret what fugacity is, but I can tell you they think too much. Okay, so fugacity is basically something that is born out of a mathematical definition, kind of a shorthand. Okay, and I'll show you here. So don't think about it too much. It's just something that appears as an artifact from mathematical definition. Okay? The Gibbs free energy is used a lot in chemical engineering, and there's a problem when we want to find its exact value. So it has there is a special treatment, okay, for Gibbs free energy, and it comes in form of the fugacity. Okay? So let's look at this. Right? We have this equation, right? So dG equals VdP. It describes how Gibbs free energy changes with pressure. Okay? We need to do something like this, you know, in order to find Gibbs free energy at different pressure, and also when we want to find the partial Gibbs free energy as well, we have to do something like this, right? Okay, so if you want to find the Gibbs free energy at a certain pressure, according to this equation, we need to do something like this. We need to add this integral, okay, VdP, from a very low pressure to the Gibbs free energy at a very low pressure as well. So P star is a very low pressure, close to 0 bar. Okay, so Gibbs free energy at a very low pressure plus integral of VdP from very low pressure to system pressure. Okay. For ideal gas, this integral can be written as RT log P over P star. That is simple, right? The problem is, for real substance, that integral is very difficult to find. Okay, that is true only for ideal gas. But for real substance, that integral VdP is really difficult to find. So we define something else here. Okay, integral of VdP from a very low pressure P star to system pressure P equals, for real substance, okay, equals RT log fugacity over P star, so that its form is similar to the form for ideal gas. Okay, we want to retain the form for ideal gas model, which is in RT log P over P star. Okay, and then for real substance, we want this term to be the correct value for this integral for the real substance. However, if we use P, it will be just true for ideal gas, not the real substance. Okay, so for real substance, we need to replace P by something else, and that something else is the fugacity F. Okay, and then according to this equation, you can tell that the fugacity has a dimension of pressure. Okay, its unit is the same as pressure in bar, for example. Okay, and now we, so according to that definition of the fugacity, okay, so we rewrite that integral for real substance into RT log Fi over P star. Now we want to find V0 gives free energy, okay, V0 gives free energy. We write two equations, okay, so one for real substance, the other for ideal gas. Then find the difference. Okay, subtract the bottom from the top. The difference on the left-hand side, Gi minus GIRG, is basically the V0 gives free energy. Okay, right-hand side is just that RT log Fi over P. Okay, using the logarithmic function identity. So if you subtracting one from the other is Fi over P. Okay. That Fi over P is defined as the fugacity coefficient of component I. Okay, that ratio, Fi over P, is the fugacity coefficient. In other words, you can also view the fugacity coefficient as a conversion factor for converting the pressure into the fugacity. Okay, so that is another way to view the fugacity coefficient. It is a conversion factor for converting pressure into fugacity. Okay, that's for pure component. We can do and then we can do the same for partial Gibbs free energy. That is a component in solution. Okay, so we do the same. We write the partial Gibbs of I equals partial Gibbs of I from ideal gas model plus partial V0 Gibbs free energy. Okay, partial V0 Gibbs free energy. And then we just rewrite these two terms as this. Okay, so that's for mu IIG. Okay, we have obtained this earlier. And then that is for partial residual Gibbs free energy. So similar to the case for pure component, the difference is that now we use Fi cap. Okay, Fi with the cap. That represents fugacity of I in solution. Okay, and then instead of just system pressure, we use partial pressure of component I over here for partial Gibbs free energy. This becomes partial pressure. Okay, so so from this equation you can see that mu IR is that term. Okay, partial residual Gibbs free energy is that term. That is also defined as the fugacity coefficient of I in solution. Okay, and Fi capital is fugacity of I in solution. So this is quite equivalent to the pure component case. Okay, and also in other words, the fugacity of I in solution can be viewed as the conversion factor for converting partial pressure into fugacity of I in solution. Okay, and the role of Hewitt equation of state is to approximate this partial residual Gibbs free energy. Okay, and then when we do that, we can just find the actual value. Okay, so the dashed curve is the values based on the ideal gas model. Then we add the residual Gibbs free energy Okay, then we can find the solid curves. Those are the actual values. Right? So yeah, this is basically what we do in this lecture. Okay, and then we use this in the second half of today's lecture in Excel. Okay, so that is the phase equilibrium criterion, right? So the partial Gibbs free energy of the same component in two phases must be equal. Okay, and then we have developed an expression for partial Gibbs free energy in the vapor phase and also in the liquid phase. So we write this for the vapor phase, that for the liquid phase. Okay, we equate the two. Okay, according to that criterion. Okay, equate the two. We see that the only difference between these two equations are those inside the logarithmic function. In other words, phi y equals phi x. Okay, or if you multiply both sides by pressure, it becomes fugacity of I in liquid phase. The liquid phase must equal to the fugacity in the vapor phase. So we can use any. They are the same. Okay, this is the phase equilibrium criterion that can be used with cubic equation of state. We can use cubic equation of state to find fugacity coefficients, and we'll do that in the second half of today's lecture. Okay, so this lecture basically leads to this equation that we will use in the second half. Okay, any question? It's 2:30 already, time for break.